Ever stop and think about what's actually powering your smartphone or your laptop or your TV? Well, the secret sauce behind all of it is a tiny, incredibly powerful material. It's the absolute foundation of our digital world. So let's dive in and unlock the secrets of the semiconductor. To really get why semiconductors are such a big deal, we got to take a trip back in time. See, before we had all these sleek gadgets, electronics had a huge problem. They were these massive, power-hungry beasts that were just, well, they weren't very reliable. So on one side, you had the technology that powered all those early electronics, the vacuum tube. Just picture a fragile glass light bulb whose job was to control electricity. They were huge, they got super hot, and they broke all the time. Now, compare that to the semiconductor. It's tiny, it's tough, it sips power, and it's ridiculously reliable. This wasn't just a small step up, it was a complete and total game changer for electronics. Okay, so what is it? What makes these materials so incredibly special? How can a tiny little sliver of silicon do the job of a big, clunky glass tube? Well, it all boils down to one single fundamental property: how well they conduct electricity. In this table here just lays it all out perfectly. On one end of the spectrum, you've got conductors, like copper. Electricity just flows right through them, no problem. On the other end, you have insulators, like rubber, which basically stop electricity in its tracks. And then right in that perfect Goldilocks zone in the middle, you find semiconductors. They're not great at conducting, and they're not great at insulating. And that right there is their superpower, because it means we can control them. This chart really shows you why they behave so differently. It all comes down to something called the energy gap. Now, just think of it as a hurdle an electron has to jump over to get the electricity flowing. For conductors, there's basically no hurdle at all. For insulators, that hurdle is massive. It's a huge wall. But for our semiconductors, the hurdle's small. It's manageable. We can give their electrons just enough of a push to get them going. But here's the secret, the part that really unlocked everything. A pure semiconductor on its own, well, it's not actually that useful. To get to its true potential, scientists had to figure out how to hack the material at an atomic level, and this process is called doping. Doping is an incredibly precise process. We're talking about sprinkling in just a tiny, tiny amount of impurity atoms, like as little as one single atom for every million silicon atoms. And get this, that tiny little change completely transforms its electrical properties, making it thousands of times more conductive. It's kind of like adding one secret ingredient that changes the entire recipe. Now, this doping comes in two main flavors. If you add an element like phosphorus, which has an extra electron to share, you create what's called an N-type or negative material. It's got a surplus of electrons just waiting to move. But if you add something like boron, which is missing an electron, you create a p-type or positive material. This creates what physicists call holes, basically an empty spot where an electron should be. Think of it like a bubble moving up through water. The bubble itself is moving, but what's really happening is the water is moving down to fill the space. These holes can move around just like a positive charge. So now we have two special types of silicon, one with extra electrons and one with these electron-sized holes. On their own, they're pretty interesting, but when you bring them together, that is where the real magic happens. This creates the foundation of literally all modern electronics, the p-n junction. The absolute instant these two materials touch, something incredible happens. As you see in step 1, all those extra electrons from the n side, they just rush across the boundary to fill the holes on the p side. This sudden meeting creates a thin layer right at the junction that has no free electrons and no holes left. And that, as you see in step 2, is the depletion region. This little region, now empty of charge carriers, acts like an electric barrier, and it stops any more charges from crossing over. This slide right here really gets to the core of it. This tiny, invisible barrier, this depletion region, is everything. It's an automatic, built-in gate, and the secret to all of modern electronics is just learning how to open and close that gate. I mean it, from a simple little LED to the most complicated computer chip in the world, everything is built on this one principle. So we've got a barrier. Now what do we do with it? Well, now we learn to control it. By applying just a little bit of electricity, we can make that barrier shrink, or we can make it even bigger. And this lets us create the simplest, and you could argue the most important, semiconductor device ever, the diode, which acts just like a one-way street for electricity. This quote on the slide just says it all, doesn't it? A diode is an electronic valve. It lets current flow easily in one direction, but it slams the door shut if it tries to flow the other way. It is the ultimate traffic cop for electrons. So how does that work? It's pretty simple, actually. If we hook up a battery in a way that pushes electrons and holes toward the barrier, that's called forward bias, the barrier shrinks and the gate swings open. Current flows. But if we flip the battery around in reverse bias, we end up pulling the electrons and holes away from the barrier. And this makes the barrier even wider, slamming the gate shut and stopping the current cold. And here's the crucial part. That gate has a key, and it takes a very tiny, specific voltage to unlock it. For silicon, which is the most common semiconductor out there, that magic number is only about 0.7 volts. Give it that tiny little electrical push, and that one-way street is open for business. Now, I know this might all sound a little abstract, a little bit like a physics lecture, but I promise you, you use this principle every single day. Let's connect this whole one-way street idea to something we all do constantly, charging our devices. The power that comes out of your wall outlet is alternating current, or AC. That means the current is flowing back and forth, back and forth. But your phone's battery, it needs direct current, or DC. That's current that flows in just one direction. The device that makes this switch happen is called a rectifier, and its most important parts? You guessed it, diodes. This visual just perfectly captures what the diode is doing. The AC power from the wall is like a chaotic two-way street. The diodes inside your charger, they act like traffic ops. They literally block all the current that's trying to go the wrong way. This forces all that chaotic energy to flow down a single, one-way DC street that your battery can actually understand and use. All right, let's do a super quick recap of everything. We started with semiconductors, these special materials whose conductivity we can control. We learned that we have to dope them with impurities to create N-type material with extra electrons and P-type material with extra holes. Then when we put them together, we get the magical PN junction, which creates a natural barrier that when we control it becomes a diode, a one-way valve for electricity that basically powers our entire world. You know, it's really not an exaggeration to say that mastering the semiconductor literally built our modern world. It powered the information age, and it put supercomputers into all of our pockets. And that leaves us with a really fascinating final question, doesn't it? What comes next? What new material is out there just waiting to be discovered that's going to define the next 100 years of technology?